this show, we're going to find out how to save lots of money on Christmas tree lights and visit a place that makes something you only see when it's 30. First, radio. I think I'm a radio.
I wonder how many Acme viewers remember this. Gathering around in the evening, looking at each other, knitting, enjoying a good program like Acme. You see, once upon a time, TV didn't have pictures. Radio goes back to, well, way back to the 19th century. If we start naming dates and times, letters will start pouring in. If you want to know who gets the credit for what, look up James Clerk Maxwell, Heinrich Hertz, Guglielmo Marconi, Edwin Armstrong, and Reginald Aubrey Fessenden. Actually, what's to invent? This is radio at its purest. This is an AM radio not tuned to a station, and this is a flashlight cell and a piece of wire. Here's a bit of strict science. Radio uses electromagnetic waves, the same electromagnetic waves that your eyes interpret as light and the same electromagnetic waves that cook your food in a microwave oven. The difference is a matter of wavelength. Lost yet? Let's dump the strict science and stick to a looser explanation. Physicists might like to leave the room for a minute. Using just a flashlight cell and your trusty Boy Scout compass, you can prove to yourself that magnetism results from an electric current flowing in a wire. Now take the following leap of faith. When the current starts to flow, the magnetic field doesn't appear instantaneously. It grows outward to its final position. Similarly, when the current stops, the field takes time to collapse. The time to form and collapse is very small, but it's there. Now imagine what happens if the current's made to go on and off rapidly. If the new field is made to build before the old one can collapse, we can start to pump magnetism out into space. That isn't exactly what happens, but it's a darn good way to feel comfortable about it. The electrical fluctuations at the center of the AM radio band are about 1 million per second, or 1,000 kilocycles, or kilohertz, or whatever they're calling it these days. Voice and music are routinely changed into electrical fluctuations by microphones, but these fluctuations are too slow to be directly useful to radio. Modern radio broadcasting uses modulated carrier waves. The transmitter creates a powerful wave at some wavelength that's been assigned to the station. For AM radio, the relatively slower voice and music fluctuations are made to vary the strength, or fancy word, amplitude of the high-frequency carrier. This is amplitude modulation, AM. Radio can be received with another piece of wire held up in the air. Trust me, this hunk of wire is currently receiving all of the radio stations in Toronto. Electromagnetic waves passing by at the speed of light are inducing little currents in it. The simplest receiver can be made with a sensitive earpiece, a long wire, and a diode. The wire goes out the window, the earpiece goes in your ear, and the diode. The received radio wave is symmetrical. The top and bottom of this picture are equal but opposite. They cancel. To recover the amplitude modulation, it's necessary to throw out half of it. That's what the diode's for. It lets current flow only in one direction. It can be used to change this into this. This you can hear in the earpiece. You have a further problem. You're now listening to every radio station in your area all at once. To tune the radio requires these, a coil of wire and a capacitor. The capacitor and coil can work together to make an electrically resonant circuit. The resonant circuit can act like a good pathway for the frequency it's tuned to and a rotten path for all others. Either the coil or the capacitor can be adjusted to change the resonant frequency. Modern radios adjust the capacitor. In a real modern radio, the capacitor looks like this. The little cans inside house the coils. To select just one of the carrier frequencies, several resonant circuits in a row are needed. In the early 1900s, radios had dials, several of them, that all had to be tuned at the same spot. In 1916, the superheterodyne radio was invented, and all radios since have been superheterodyne. The superheterodyne receiver fixes its reception at one frequency. It's 455,000 cycles per second for AM radios. At the antenna end, a circuit converts the station of interest to that intermediate frequency. This saves having to adjust several resonant circuits in concert. They're fixed at the factory. You might have tuned a guitar by listening to the beat note you get from two similar notes. When you tune a superheterodyne, you're actually tuning a small radio transmitter that beats with the incoming carriers to make incoming carriers plus harmonics of incoming carriers. The harmonic that happens to end up at the internally resonant setting is the station you hear. The resonant row of circuits is called the IF strip. IF for intermediate frequency. Now, if you believe absolutely none of this, use one superhet to confuse another superhet. Place two radios together, turn one up, not tuned to a station. Keep the volume off on the other, and tune this silent one. Now, I have no way of proving to you that the sound's coming from the one I'm not touching, so you'll have to try this yourself. FM radio uses all of the same stuff, with one big improvement. Static can be heard on AM radio because of all sorts of random electromagnetic disturbances. They'll add to the carrier and become part of the modulation. In FM, instead of the modulation varying the carrier wave strength, the modulation varies the carrier wave's frequency. So FM 104 is only nominally at 104 million cycles per second. The music and voice on FM 104 is wobbling the carrier frequency to either side. To detect this kind of modulation doesn't require a diode. It practically detects itself. As the carrier passes through resonant circuits, it rises and falls in strength proportionate to the frequency wobble. To eliminate static, the received carrier wave is sliced electronically, and the top and bottom, containing any superfluous junk, are discarded. The original frequency modulation is still there. TV is broadcast using an AM carrier for the picture and an FM carrier for the sound. These two carriers are always a fixed distance apart in frequency, and as a convenience, you tune both at once. Originally, it was intended to have two IF strips in a TV receiver, one for picture, one for sound. It was a black day when some genius figured out that the sound and picture could share one IF strip to save money. The problem is that the two carriers do a bit of their own heterodyning in the intermediate frequency strip. You might not have known the reason, but you've experienced the result. Bright scenes and white titles buzz on some sets. Don't blame science. Blame progress.
Darn. Missed the thing commanded. Rotate.
Okay, what is this? If you said plate glass, you're out of date. Since the 1950s, the float glass process is responsible for most of the large windows you see. This is AFG glass in Scarborough, Ontario. Float glass starts out like all window glass, as silica sand, soda ash, dolomite, limestone, and a couple of other earthy ingredients. Glass that's broken during the manufacturing process is added too. The carefully mixed ingredients are called frit. The frit is fed slowly into one end of a huge furnace and gradually blends into the sea of molten glass inside. The added broken glass actually melts at a lower temperature than any of its parts. This speeds up the melting process and saves energy. The walls of the furnace are made from 18 inches of brick. Inside, the river of glass is 4 feet deep. This thing that looks like a video camera is actually a pyrometer, measuring the temperature of the furnace. It's about 1600 degrees Celsius in there, at the hottest part. These are stirrers. From the furnace, the molten glass flows to the float part of the process. Glass is slowly and continuously poured onto a pool of molten tin. Floating the glass on molten tin is a tricky process, but it has its rewards. Tin melts at a considerably lower temperature than glass, so glass can solidify as it travels across the tin. At the end of the float bath, perfectly flat, fire-polished glass will come out in one wide, continuous ribbon. This method of making window glass has all other methods beat, hands down. The top side of the ribbon is covered in a blanket of hydrogen and nitrogen. This is to prevent the hot tin from oxidizing. Inside the beginning of the float bath, the glass is the consistency of very warm toffee. Toothed wheels grip it and move it along. These are the motors that drive those wheels. They can be repositioned to control the width of the ribbon. This thing that looks like a video camera is a water-cooled one. The control room not only controls the entire process, it gets a great view of it, thanks to the water-cooled cameras here and there. This one's looking back towards the beginning of the furnace. Every 20 minutes, the furnace changes its firing direction to keep the heat evenly distributed. This would look great in color. These are the gripping wheels. Officially, they're called attenuators. The attenuators are running at a slight angle to the ribbon, pulling it out to its final width. This chart is recording the exact width of the ribbon. A couple of hours before we got there, the ribbon width had been changed. The chart accentuates minor variations. The glass ribbon leaving the float chamber is solid enough to travel on rollers without being marked. It will travel the length of a football field in this annealing layer. Annealing is controlled cooling and serves to relieve stress at the molecular level. This is our first clear view of the ribbon. In the old days, someone would stand here signaling defects in the glass. These days, automatic monitoring equipment does the job. The ribbon is remarkably flat, clear, and even, except for the pinch marks from the attenuator wheels that controlled it as it floated on the molten tin. You'll be pleased to know that your windows are now washed at the factory. Too bad they don't stay washed. The ribbon is cut into sheets here. The cutter is traveling diagonally because the ribbon's moving. The result of the movement and the angled cut is a cut at perfect right angles to the ribbon's edge. The cutter's just scoring a line, like a handheld glass cutter does. A little nudge causes the glass to break along the scored line. The pinched edges are cut off next. Most of us are conditioned to hear the sound of breaking glass and say, "Uh-oh." It took us a while to stop jumping every time an edge was trimmed. It sort of sounded like the Little League practicing in front of a store window. Broken glass goes back to the furnace. After being cut and trimmed, the sheets are finished. No further polishing or treatments required. Sheets of glass with small defects are, well, back to the furnace. Making float glass is a continuous process. Automated machinery makes sure that the product is stacked at various locations and in the proper sequence that will allow time for the accumulating piles to be handled. One handy accessory for a float glass operation is a big warehouse. It's a big job to stop the process and restart it, so you make glass. When the construction industry goes through one of its periodic slowdowns, you store glass. Glass that's inadvertently damaged in handling gets, well, get a load of this. I wonder how long it takes for this job to feel routine. From the warehouse, these sheets will go to various manufacturers to be made into everything from mirrors to double-glazed windows. Acme thanks AFG Glass for a great visit. If you'd like to show your appreciation to them, send the kids outside to play baseball. Okay, all together now. Where's the present flippity chip stupid? First of all, with the price of these things, it really isn't worth trying to fix them. Buy new ones. Somehow that idea goes against everybody's grain. I mean, after all, a simple string of lights would seem to be the kind of thing that anyone could figure out. And if we all simply threw them out every year, the landfills would be full of them by the next generation. So go ahead, satisfy that urge, and keep them in good repair from year to year. Acme would like to tell you what you're up against. These are easy. Each lamp operates on 120 volts, and the lamps are all wired in parallel across the two wires, and the whole thing plugs into 120 volts, and if a lamp burns out, you replace it. But the only repair you can make on a set like this is to bend up the little bottom tab a bit. You do that with the set unplugged. Some fancy bulbs don't quite screw all the way in, and bending that tab up will occasionally help. These strings are cheap and pretty. Thus ends their good qualities. These delightful little darlings are series strings. The bulbs operate on less than 120 volts, and they share. Here are two 6-volt bulbs operating on 12 volts. I've wired them in series. The current comes from a power supply to the first bulb, and then through the second bulb and back to the power supply. Old-timers will recall what happens in a series string when one of the bulbs burns out. There's a broken circuit, and all of the other lights in the string are extinguished. Doubting Thomas, get back in your seat for a minute. It's important in a series set that all of the light bulbs are identical. If they have different characteristics, the applied voltage won't divide evenly among them. Miniature Christmas light strings use differing lamps. If the string simply had 10 lights, they'd be 12-volt bulbs, because 10 times 12 equals the 120 in the wall socket. By the same math, a 50-light string would require a 2.4-volt bulb. There are different bulbs with different characteristics for different string layouts, so you'd be advised to label the sets when you buy them if you're planning on buying replacements in 3 years. Putting the wrong bulb in a series string either puts a strain on the improper replacement or on the rest of the bulbs in the series, depending on which way you make the mistake. In any and all events, a dead bulb in a series string should be taken as a harbinger of bad things to come. Okay, Doubting Thomas, speak up.
How come when one of those light bulbs burns out, the rest don't go out like you said they should, Dave?
Herein lies the mystery. These little bulbs are unlike every other bulb in the known universe. When they burn out, they're designed to become a short circuit. Usually, the failure of a bulb's filament results in an open circuit, no current flow, and the old-fashioned series string lights would all go out. These little devils have an internal structure something like this. When the filament finally fails, the two supports touch each other to keep the current flowing to the rest of the string. It's a recipe for disaster. When one bulb fails, the rest will share the added voltage. This is a chart I recreated from a lighting manual. It plots light bulb life against percent of rated voltage. Notice it isn't a straight line. By operating a bulb at 90% of its design voltage, the life is increased out to 400% almost. The reverse is just as dramatic. Operating a bulb at just 110% of its design voltage will reduce its life to only 20%. That's not by 20%, that's to 20%. When a lamp fails in a series string, it shorts to keep the rest of them lit, and its voltage will be shared equally by all of the other lamps. This will raise their voltage. With one lamp gone in a string of 20, It's a small percentage increase, but it's shortening the life of all the others just a little. By the time 3 or 4 have burned out and self-shorted, the entire rest of the string is seriously threatened. So, what have we learned? Well, if you see just one burned out one, change it fast. If you have a completely dead string, one of 2 things has probably gone wrong. If you were sloppy about replacing burned out bulbs, it's likely that the entire group of bulbs is now blown. Because of the modern miracle of blister pack retailing, it's cheaper to buy a whole new string of lights, not to mention saving the landfill from 8 more blister packs. The other possibility is that 1 or more of the bulbs are, shall we say, loose. The sockets on these things were designed in the true spirit of Christmas. It's a miracle that they make contact in the first place. To be fair, it's what keeps them cheap. 2 small glass wires come out of the glass bulb and are bent around the plastic base. These 2 wires make contact with a pair of fingers in the socket. Study the dead set carefully. If it looks like a miniature Chernobyl has occurred in each one, they're probably self-destructed because you were too lazy to change the burned ones. If they look physically okay, it's worth giving each one a gentle push and a twist. Sometimes 1 or 2 aren't making contact. Remember though, because of the self-shorting feature, it's least likely that 1 bulb is burned out if the whole string's dead. Also be aware of those delicate wires that attach them if you're changing them. Factoring all of the above into the Acme supercomputer arrived at the following conclusion. Pick up a couple of spare strings when you shop for your wrapping paper.
Yep.
In the next Acme, along with the usual boring science stuff, we go to Toronto's CN Tower and snoop behind some closed doors. We even got them to open up the floor in the revolving restaurant for us. I love this job.